Good morning, everyone, or whatever time of day it happens to be for you. So before, as Merle says, I tell you what a maverick is, I want to highlight that the broader problem within which I'm talking about here is the role of diversity in collaborative problem solving. And doing science is problem solving. It's a wonderful example of problem solving. So generally, I'm going to be framing my examples and my discussion as though I'm focusing on the role of Mavericks and diversity in doing science. But I think I am ultimately talking about problem solving generally. I should also say that when I'm talking about diversity here, I'm talking about cognitive diversity, because that's what's in all of these models. So that's diversity in knowledge, interests, abilities, cognitive styles, beliefs, perspectives. I'm not talking about demographic diversity today. Obviously, that's an extremely important topic. And quite apart from issues of justice and fairness, it does interact with the cognitive issues I'm talking about. But we're abstracting away from that in running these computational models that I'm talking about. So evidence has been building up over decades that science works better when we're not all the same. So for instance, we shouldn't all converge on the same optimal approach. Even if there's a theory or a method or something out there that is impactful, hard-hitting, benefiting society, going to get you published in Science, it doesn't mean that we should all latch on to that. Science as a whole, the group level outcomes will be better if we still pursue different things. We shouldn't have all the same priorities. Discovering new things is different from showing that things replicate. And it's very difficult to do all of that. And we need people to be invested in doing different aspects of this broader project. And we also shouldn't have access to the same people. If information spreads very quickly through a network and we know what everyone is doing at all times, then it's easier to latch on to the apparent optimum. And this can increase herding, for instance, or groupthink. So it's actually useful if we don't contact the same people, if basically if the flow of information is throttled in some way, if communication is throttled. So diversity is useful for problem solving, like doing science, but what kinds of diversity is my broader question. The two core factors that underlie all of these examples I've been talking about are firstly, how people gather information, and secondly, how information flows between people. And at the nexus of both of these is learning strategies. So learning strategies will affect what you're learning and how you're learning it, who you're learning from. And so potentially learning strategies or diversity of learning strategies is going to be an important part of the broader picture of how diversity benefits problem solving. So the question is diversity in learning strategies important for things like collective problem solving? So what do I mean by diversity in learning strategies? Well, there are several ways to look at it. And one way is to talk about these two broad classes of strategy. One is individual learning, where you learn directly from the world via your individual experience. So for instance, let's say I want to find the best restaurant in Munich. If I'm doing individual learning, I will go out and try a bunch of restaurants to see how good they are. The downside is that this is time consuming and expensive, and it's also risky. I might end up trying a bunch of bad restaurants to find one good one. On the other hand, there's social learning, which is learning from others. So instead of trying a bunch of restaurants, I can just get on the internet, get on Google, and look at some reviews, other people's experiences of restaurants. And that might make it a lot easier for me to find apparently the best restaurant. So copying other people is very efficient. On the other hand, this adds no new information to the group. Someone has to be trying restaurants at some point. So you really need both of these. And if these are on a continuum, we might call the extreme individualist a maverick and the extreme social learner a conformist. So we know that there is stable variation in people's social learning strategies. So for instance, some people are stably more maverick-like in their approach, and other people are more conformist. So we know that there is variation on these strategies. We also know from previous computational models that having a small number of Mavericks helps the group as a whole. Mavericks are useful for group problem solving. So it seems like the answer to my initial question is yes. It seems like diversity in social learning strategies is useful for group level outcomes. But not so fast. The current research doesn't actually show that. So I'm going to quickly outline how this family of models works. I'm going to show why they don't actually make a positive argument for diversity. And then I'm going to show how you can tweak them by adding one missing ingredient that will, in fact, leverage diversity in social learning strategies to benefit group outcomes. All right, so these models typically assume some kind of epistemic landscape. There's an example on the screen there. So the landscape here, the ground coordinates basically represent different approaches, different frameworks, methods, theories, etc. And the height, the peaks, represent the epistemic value, how much we've learned, how good our science is, the benefit for impactful science, etc. The epistemic value of each thing. So for instance, you might, so this landscape, for instance, has two peaks. So for instance, let's just say this is the epistemic landscape of studying one particular disease. There might be multiple ways of treating this. Most of them might not have a great effect. Some of them might only treat the symptoms rather than the cause. Some of them might have negative side effects. So let's just say in this landscape, there are two optimal treatments for this disease. And the challenge is to find them, but not just find them. The aim here is not just to discover those two peaks as you are wandering around this epistemic landscape. The aim is actually to excavate as much of the landscape as efficiently as possible. So what I mean is, if people are wandering around this landscape trying to find a cure, it's not just that they have to get to the theory or the approach where the cure is. They have to do some work when they get there. They have to do some research and then publish a paper. And once they've done that, that peak is less useful because we know something about it already. And one reason I'm interested in that, and one reason it's particularly interesting for this venue, is that this addition that needs to excavate some of the landscape adds a pressure for coordination. Without that need, if it's just discovering the peaks, then you could just have two people discovering the peaks on their own without coordinating with anyone, and that's great. But if you need to excavate the landscape, then it helps to have other people follow you and help you excavate the thing that you've discovered to get the cure out to society as quickly as possible. Okay, so in this landscape, you have simulated agents who are wandering around looking for the best thing that they can find. They start on a random spot and they move in a random heading. And they have a basic exploration strategy, which is if you're traveling around this landscape and your heading involves you staying flat or going uphill, in other words, having success, you just keep going with your heading. But if you go downhill, if you start failing, if you are starting to find an area of the landscape that is worse than where you were, you pick a random direction. So this is what it might look like. There's a little agent, that's the dot that is moving around this landscape. And you'll notice this agent tends to stick to the higher parts of the landscape and avoid the valleys. They may dip into valleys occasionally to jump over to a neighboring peak. One thing I should say is that this landscape wraps around on both sides. So if you exit bottom left, you'll come back in top right, for instance. It's effectively a torus. What the excavation adds is something like this. So as you're wandering around, I don't know if it's easy to see on the screen. I know Zoom worsens the qualities of these videos, but the landscape under that agent is being excavated and is lowering. So once you've published your paper, there's less there. Obviously, if there's a higher peak, then there's still something to excavate. Okay, and this is how you implement a social learning strategy in this kind of framework. So if you're going downhill, if you're not succeeding, what you do is you find out, is anyone else doing better than I am? So you see if social learning might be beneficial for you. And you calculate the potential gain of the other people on your landscape. So important here, the gain is not just how high they are, if they're on the peak or not, it's also their distance from you. So if someone's on a peak but very far away, you might not gain much because you'd have to travel quite far to get there. So effectively, gain here means slope from your current position. So every agent has a social learning threshold. And if the potential gain is higher than that threshold, you set your heading for that target. Otherwise, you carry on with individual exploration. So for instance, this agent is a Maverick. They have a very high threshold, which means effectively a narrow cone. And so they're not interested in most things. It's very hard to catch their attention. So that's why they're a Maverick. On the other hand, this person has a very low threshold, a very broad cone, and it's quite easy to get their attention. And they may end up following someone else quite easily. And this is a sort of intermediate position. Okay, so putting it all together so far, how these models work is that you start in a random place on one of these landscapes with a random heading. You do some individual learning, which is some local random hill climbing. If you start failing, you see how everyone else is doing. And if someone is doing better than you, and the gain from following them is above your social learning threshold, you will head their way. Otherwise, you'll just carry on with individual learning. All right, so this is just replicating previous work here. So this is what it looks like if everyone's conformist. So these are the little agents wandering around the landscape. They all quickly herd onto that central peak the minute someone has discovered it. And the thing about conformists is that they tend to stick close. So they've excavated that peak. There's nothing else to gain there, but they're not really exploring the rest of the landscape. They're still stuck close together because they're conformists. On the other hand, if you have some Mavericks like this, they will discover both peaks. It might not be easy to see here, but there's a central peak. And then because there's a torus, the thing sticking up in all corners of this landscape is the same peak. It's a second peak. And so Mavericks are more likely to discover that second peak, for instance, and excavate both of them. You can see, though, this is more inefficient. They're excavating more slowly because there are fewer of them there. So again, just replicating previous findings, conformists tend to discover a peak and excavate it quickly, but then they plateau. It's very hard for them to spread out across the landscape and discover a second peak. On the other hand, Mavericks are more likely to do that. So this is what we know so far. So it seems like diversity, having some Mavericks and some conformists might be a good idea. One thing you can add to this kind of model is graded social learning. So for instance, a low number here is a low threshold, meaning you're a conformist, and a high number means you have a high threshold and you're more of a Maverick. And having a higher threshold overall is better because then the group is more likely to discover the second peak. Okay, so the first question, is this really telling us anything about diversity? And the first thing I add to previous models is this difference over here. So imagine each dot represents an agent. You can either have a heterogeneous or diverse population like the red on the left, where we, let's say, have 2 Mavericks and 8 conformists, or we could have a homogeneous population like on the right in blue, where we have everyone with the same social learning strategy, mostly conformist. The important point here is that the mean social learning strategy of both groups is the same, and that's in the dotted black line. So they have the same group mean social learning social threshold, but in one, everyone's on that mean, and the other one, they're spread out around that mean. Now, if you implement this, which is the difference between the 2 panels here, heterogeneous or diverse versus homogeneous or non-diverse, there is no difference. Being more Maverick in either case is useful, but it doesn't matter if you're spread out around the group mean or everyone is on the group mean. So in other words, there's no benefit to diversity really, according to the current literature, even though they make a claim for a benefit. So the next question is then, what, if anything, could leverage diversity? Can we do anything to see why diversity might be beneficial? And to do this, I'm adding one parameter, which is called tolerance to failure. So an individual with tolerance T will only pull others if going downhill by more than T. So previously in the current literature, what happens is if you're going downhill at all, meaning your current position minus your previous position is less than 0, you start, social learning kicks in and you check if the gain is above your threshold, so your particular threshold. Now it's just that the same thing needs to be less than threshold T. So in other words, you can if you have a higher threshold, you can handle going downhill a little bit before you start panicking and checking how everyone else is doing, if anyone's more successful than you. So the basic message is that adding in this one parameter does leverage a benefit of diversity. So in blue is the homogeneous population. This parameter tolerance has no effect, but in the heterogeneous diverse population, increasing tolerance does have an effect. And as you can see, the y-axis is the amount of epistemic benefit here, and it's higher for higher tolerant groups. So just to be very, very clear, the current literature is sitting at x equals 0 on this plot, and that's why there's no benefit for diversity. Whereas in fact, as you move away from x equals 0, there is a benefit for diversity. So in other words, tolerance to failure is an important part of the picture that's currently missing. So what actually does it do? One of the really interesting things is that it has this synergistic boost on conformists. So if you compare the two panels here, the heterogeneous and the homogeneous populations, the color is showing you the social learning threshold. So red, lower down, is more conformist, and blue, higher up, is more maverick. And so you can see the benefit for diversity in a more maverick population. The change from the right to the left panel in the blue line is not huge. But there is a huge change in the red line going from the right to the left panel. So in other words, having this tolerance of failure doesn't help conformists if everyone has the same mean. What it does do is, if there are some mavericks around, those conformists benefit massively from this boost to tolerance. So how is this affected by having a variable social threshold or a variable strategy? And the point here is that realistically, we know from real world data that our learning strategies are variable. No one is 100% maverick all of the time. No one's 100% conformist all of the time. After many failures, even the most stubborn maverick might look to others for help. In fact, one thing that's known is that the more difficult the problem, the more likely we are to fail, the more likely we are to rely on social learning. So next I had a parameter resilience. And what this does is that at each failure, you decrease your social threshold by R. It's a multiplicative effect. So your new threshold will be R times your previous threshold every time you fail. So that just is implementing the real world finding that the more we fail, the more likely we are to just look around and see what everyone else is doing. So we have a lower threshold the more we're failing. So resilience is on the x-axis there. So in other words, the current literature is sitting at x equals 1. This x parameter is showing a little bit more of the space of possibilities. It's not very obvious here, so I'll skip to the next plot quickly. But it looks like there may be a hint that the red line is slightly shallower, slightly less steep here, which means that having tolerance to failure in the model might make you more robust, more resilient, in other words. So adding in an explicit index of tolerance to failure here. So the panels represent tolerance to failure, increasing as you go from left to right. Again, the current literature is sitting in the left panel where tolerance to failure is 0. As soon as you start increasing tolerance, this was the previous finding I mentioned, now you get an effect of diversity, a benefit to diversity. But one other thing you can see is that the rightmost panel, that the negative effect of resilience, the negative, negative as you go down, but I guess it's a positive slope. But at any rate, the slope of the red line in the rightmost panel is shallower, So in other words, the cost of being non-resilient is less bad for you if you are in a diverse group with some tolerance to failure. I'm going to skip this just because that's getting complicated. And finally, one question is, what kinds of problems does this all matter for? So this is not an innovation. This is a thing that's typically done, is having a noise parameter. So the left panel there is low noise and the right parameter is higher noise. And just in case it's not easy to see these dark blue shades on your screen, the landscape on the right-hand side is rougher, more variable, less predictable, more complex is what it boils down to. And so one really interesting finding is that this benefit for diversity of having some tolerance to failure is spiking in the middle for moderately complex problems. It's there for more complex problems, but it's just really exaggerated for moderately complex problems. And this is a 3 or a 4-way interaction, I can't remember, but at any rate, there's a lot of information here, so let me just talk you through it. The interesting question here is, when is there a benefit for diversity? In other words, where is the red line furthest from the blue line? And having tolerance, which is the main new parameter I've added as your x-axis, you can see that an increase in tolerance really leverages diversity for middlingly complex problems, which is in the middle at noise 6, but also when your population is mostly conformist. So it's your social threshold, that's the rows going down. So the top row is people are on average more conformist, and the bottom row is people on average are more maverick. And the thing is that realistically, we know mavericks are rare. You're not going to get a population that's 50% maverick, 50% conformist. Mavericks are just not that common. So in the real world, the top row is the more likely kind of scenario. And so tolerance gives you a bigger boost to diversity for moderately complex problems, that's the middle column, and in realistically conformist society, that's the top row. So what have we learned? If you add tolerance into these models, when it comes to group level benefits, diversity in social learning is tightly bound up with diversity in values. And that's what tolerance of failure really is. You have to not mind failing so often. You have to mind not having a great paper to publish every few months if you're going to be a maverick. There is a cost to you. The next thing we've learned is that, well, we know previously people aren't resilient. What we've learned is that combining this tolerance of failure with diversity can reduce the negative effect of having lower resilience. And we've also learned from the noise parameter that there's not much difference for these things on easy problems, but for moderately complex problems, the boost to diversity of tolerance is large. I'm out of time, so I'm going to skip the future work and just leave you my research question and my answer over there. And I've not been following the YouTube thing, so maybe Merle can tell me if there are any questions.
First of all, thank you, Justin. We need to thank our speakers first before we jump into the heavy questions. That was wonderful. Thank you so much. And it is true that the many interactions on the penultimate slide made for some inspiration. Like I have to think a little bit to try and capture all of that. But your summary was perfect, so I have screenshotted that for myself to have a think about that. I have to give YouTube a chance to catch up because we're a little bit ahead of the YouTube stream. Bahar actually says she has so many questions, so that's just popped up. Here's one. How about when you add individual gain relative to group gain? And another, any ideas on how to move this modeling work to experiments?
Right, two very, very good questions. I read the individual gain versus group gain. I've not really looked at that. I will ultimately start expanding this model, but one reason I haven't is that we know from previous work, a paper by, I forget her first name, but her surname is Thoma, 2015 in Synthese, shows that basically Mavericks, on average, have very little individual gain. So in other words, for all of this to work and for there to be a benefit of diversity, you need people who are okay with that. So yeah, it will be useful to combine these two previous approaches to the model. One about the excavating the landscape and me having added tolerance to diversity, and the other strand in this tradition, which is what about individual gain? And yes, I do hope to combine those. Moving this to experiments, I ultimately would like to set people a science-like task where you have to generate hypotheses and then test them. I'm reluctant to do that until I know more about this parameter space, because, you know, as you could see from that complex series of plots at the end, there are lots of parameters, and we need to know a lot more about how they work. And I need to be more confident about that before I start worrying about experiments. But, you know, I'm primarily an experimentalist who just does some modeling when there's a complex question that I can't do experiments on yet. So ultimately, I will definitely be bringing this back to experiments.
And I have a question for you. You mentioned right in the beginning, well, not in the beginning of your talk, but before you started talking about resilience and tolerance, you mentioned that people, when they enter this landscape, they do an individual search first, and that at some point they decide to move into a social mode. And obviously, some of those same factors will become relevant, but one of the key topics of discussion over the last few days has been this idea of transitions, which seems so important because they might give you an indication of strategies people use later. And maybe the trigger that switches you from an individualistic to a more social learning strategy to begin with is actually how you decide later on whether to continue to seek social information or not. So I wonder if you have any insight into that very first transition.
It's, to be honest, one thing I'm really struggling with the current literature on this, because there are some experiments that make it look like the human default is to be a maverick, to try your own way before you basically cave in and see what everyone else is doing. But on other experiments, they seem to show that the human default is to be a conformist. We are a very social species. And there is this glaring contradiction in the literature using different tasks and different approaches. And we need to know a lot more about what a maverick is or how these strategies work. And yeah, basically, this is just a huge current gap. And I think the major gap is understanding the task properties, because there are different traditions showing, you know, people are basically maverick versus people are basically conformist. And they use very different tasks. And it's really hard to compare those until we can build some kind of parameterizable halfway task where we can make it more like that one or like that one, depending to try and pull apart this apparent contradiction.
Do you currently model that transition point, or when you have your simulation, is it just that they basically, once they're in the landscape, they switch into a social mode?
So they just start out with some random threshold that depends on the parameters, depending on how high I want to make the population average.
Okay.
So the beginning here is just kind of set for them by me. And how quickly they transition to social learning in this case is dependent on something like the ruggedness of the landscape. If it's a fairly smooth landscape, they have a higher chance of either going flat or going uphill. And so they will continue in their initial trajectory for some time. But if it's a very rough landscape, they will start going downhill pretty soon. And so they're more likely to start social learning. And this is consistent with a lot of what we know from cultural evolution, which is really where social learning is, I think, most sophisticatedly studied. This particular dimension is most sophisticatedly studied currently, which is that the complexity of the landscape, the ruggedness of the landscape is one thing that will affect what the baseline is, the starting point, in other words. So yeah, I guess the short answer to your question is it probably mostly depends on the ruggedness of the landscape, the task complexity.
So I think that's a great place to basically put a bookend to this session. We started with Pedro Passos talking about a similar idea that depending on the field that you're playing on and the context of the task at hand, you very much vary which kind of coordination strategies you might use and what we as experimentalists might want to measure. And then we've also had this common theme over the last few talks about updating. When do you use information and how do you use that information? So thank you so much, Justin, for bringing us to a close here in the morning session. We have a workshop.